you please introduce yourself and your area of research?
My name is Ajith Parameshwaran. I work in this area called Gravitational wave astronomy, which is the idea is to use the observation of gravitational waves to study the universe. It is the newest branch of observational astronomy.
Can you explain what is gravitational waves?
Yeah, so maybe it's useful to make an analogy with light. We see light is electromagnetic waves. This is basically freely propagating oscillations in the electric and magnetic fields. So similarly, gravitational waves are freely propagating oscillations in the gravitational field. However, it turns out that gravitational field is basically a manifestation of the curvature of space and time. Okay. In the presence of gravity, space is curved and time runs slower. It's a bizarre idea, but it's a prediction. It's a postulate by Einstein's theory of general relativity. It's not just a prediction; it has been verified by a large number of experiments and observations. Now, gravitational waves are even more bizarre. These are time-dependent changes in the curvature of space. So you can imagine them to be ripples in space-time, just like you have ripples in a pond, ripples in the water.
But Einstein declined that gravitational waves existed, right? He
Okay.
gave it a paper.
The history of gravitational waves is rather complicated. The reason is that general theory of relativity has this very intrinsic property that the physics is independent of any coordinate system that you use. In fact, it is a universal principle. This means that depending on your coordinate system that you choose, you can get certain artifacts which are not there in the nature. So whether the gravitational waves, so the ripples in space-time, or propagating waves in the space-time curvature, is an artifact of a choice of a particular coordinate system or a real physical effect. There was a lot of confusion in the early years. So Einstein has first proposed it, then he retracted it. But then a huge amount of work by mathematical relativists in the earlier half of the 20th century confirmed quite clearly that gravitational waves are really a physical effect, just like electromagnetic waves.
Okay. So you have worked on LIGO, right?
Yes.
Can you tell us about that?
Yeah, so basically, LIGO, the Laser Interferometer Gravitational Observatory, are the large observatories that measure the passage of gravitational waves in the Earth. So when gravitational waves pass through the Earth, they make small changes in our space-time. So basically, they stretch the space in a particular way and compress it in a particular way. So that stretching or squeezing of space is like tidal forces. Now, it is, for example, just like how the moon creates tides on the Earth. Right? The Earth is usually a spherical object; it gets deformed. One direction gets elongated, other direction gets compressed. These are characteristic in nature of tidal forces. And gravitational waves exactly do the same thing to our space. It stretches the space in one direction and compresses the space in another direction. But it's a very, very, very tiny effect. That effect is like 1,000 times smaller than the size of an atomic nucleus. It's like a very, very small effect. So to make these extremely small changes in the space, one has to make these very large detectors called laser interferometers. So LIGO is one of the first of such instruments, which is what is called a Michelson interferometer, about 4 km by 4 km. It's an L-shaped detector. It is able to measure extremely precise changes in the geometry of space due to the passage of gravitational waves. There are 2 detectors in the US, the 2 corners of the US, separated by about 3,000 kilometers. There is a sister detector in Europe called the LIGO. And we are in the process of building a third LIGO detector in India called the LIGO.
Okay. So the first gravitational wave was detected in 2015, right?
Yes.
So you were working on that before that.
Yes.
How did it go? What was the history behind the first
What
discovery?
Was
what was the story behind the first discovery?
Okay. So I have been part of the LIGO observatories for a fairly long time, from 2004, since I was a PhD student. And I have analyzed the data of the previous generation of LIGO detectors called the initial LIGO. So we have had several data taking runs. We have analyzed years worth of data and we have found no signals. So it is very difficult to believe when this first signal came that it was a real signal. Because in order to make sure that our data analysis pipelines and algorithms work well, we create fake signals in the data and put in the data. Our scientists and colleagues in LIGO can create fake signals, fake gravitational signals, and inject in the LIGO data. And this is to make sure that our analysis algorithms actually pick them up. It's a way of testing this. It's called these are called software injections or hardware injections. You can actually change the arm length of the LIGO detectors that would mimic the passage of gravitational waves. It's a hardware injection. And most of the time, these hardware injections are known to everyone. The analysts know about there are such injection signals in the data, etc. But sometimes, to avoid our biases, some blind injections are also put in the data. So, for example, only a small number of people know that a number of such signals are injected in the data, and they won't tell you where this signals are in the data, etc. And the rest of the collaboration goes on analyzing it, find the signal, and only at the end we would know that this is a blind injection. In fact, in 2009, there was an event, and the whole collaboration went about, even wrote a discovery paper before we opened the envelope and found that it was actually a blind injection. So the first response to all of us who were working on this was, this is a blind injection.
Okay. It was the one in 2015.
Too pessimistic. Yeah, we were in 2015. So I remember I was, in fact, in 2015 of September, I had gone to a LIGO collaboration meeting in September. I had just come back a few days before, and I was on vacation in Kerala. And then I got this call from my colleagues, my CTS, to postdocs at the time, and who told me there is this event that came out of LIGO. I said, yeah, fine, it's just section. But then we were actually with one of the first graduate students at ICTS, Ajith Ghosh, and our postdoc Ajith Parameshwaran, etc. We were developing a very interesting test of Einstein's theory that we would hope that maybe after 5 years, when we have detection of gravitational waves, we'll be able to use the observations to test Einstein's theory. The idea is that if you observe a signal from a coalescence of binary black hole, etc., by studying the nature of this particular signal, we are able to test whether Einstein's theory is correct or not. So we were developing this test, but it turns out that the signal was particularly appropriate for applying this test. So I thought, okay, whatever, there's a fake signal, but let's anyway run our analysis on this data. So my colleagues here ran that analysis. The analysis was actually ready to go while I was continuing to go on vacation, not bothered by this signal. But then subsequent analysis, and it turns out that it was not an injection. It turned out to be the first observation of the real gravitation.
It was real. What are some of the surprising findings from your research into gravitational waves?
So these gravitational waves now, it was essentially first was developed as a way of testing Einstein's theory, but now it is now opening up a new branch of astronomy. So we are able to see the universe through a different light. In fact, we organized an event at ICTS in February 2016 when the announcement of the discovery came out. This event was called Universe in a New Light. So essentially, we are able to see the universe through a different window. And many objects that we are unable to observe using light, which is the main tool for observing the universe, we can now observe using gravitational waves. And one classic example is these binary systems of black holes. The universe is, in fact, littered with a large number of black holes. Many of them are in binary systems. They would orbit around each other. And they emit gravitational waves. They would come closer and closer. They would collide. And they emit a burst of radiation.
After the collision, the gravitational waves are formed?
No, even during this in spiral, you get gravitational waves. The merger is the largest part, but then it forms this single black hole that would oscillate, producing what is called a quasi-normal mode oscillation. Gravitational waves, and eventually would quiet down. So it's the first time we are able to observe such events, and this is only possible through gravitation. So in the last 8 years, we have now published the discovery of about 100 such gravitational wave signals coming from such binary mergers happening at different parts of the universe. In fact, the ongoing observing run have observed another more than 100 signals. We are increasing the number of observations. So we are now able to now do demographics of black holes. We know we can study what is the distribution of the black hole masses in the universe. We can do population studies of black holes. And one big surprise that these observations brought out about that there are a much larger number of very massive black holes that were much more massive than we thought that black holes are. So, for example, the previous observations of black holes were from our own galaxy. They all have about 10 solar masses, 10 times the mass of the sun. But the black holes observed by LIGO and Virgo are on average much more massive. They are about 50 solar masses. There are these giant black holes, and it is not entirely clear how nature produces them. There are one such puzzles, for example. And similarly, we have observed the collision of two exotic stars called neutron stars. And this merger not only produced a gravitational wave signal, but also produced a flash of electromagnetic radiation, flash of light in different wavelengths of electromagnetic radiation, starting from gamma rays, very high energy gamma rays, all the way up to very long wavelength radio waves. So we are observing the same phenomena, the merger of the neutron stars, using multiple messengers, using gravitational waves, using X-rays, gamma rays, optical light, radio waves, etc. It's called multi-messenger astronomy. We are observing the same phenomena using multiple messengers.
But how is gravitational waves giving different perspective of looking at the world?
Very good question. So it turns out that gravitational waves are produced by large disturbances in the space-time. It is produced by the motion of these extremely heavy objects, like these neutron stars. So they are produced by the coherent motion of extremely large and massive objects. While electromagnetic radiation are typically produced by oscillations of charges or accelerating charges, etc., the surface of these objects. So they are seeing very different aspects of the same phenomena. So if you want a particular example, if you see, we have seen these collapsing stars producing supernovae. We see every 50 years or so in a galaxy is supernovae. And the light is produced by the surface of these objects, while the gravitational waves are produced in the interior of these collapsing objects. They carry very different information. They are complementary. So if I make an analogy, observing light, studying electromagnetic radiation is like seeing, while observing gravitational waves is more analogous to hearing. They contain very different information. So the multi-messenger astronomy is like a multimedia video. You only see both video as well as audio.
I went through your article. There was the sound of gravitation wave.
Yeah.
How did you guys get?
Yeah, it's just like you can the X-ray image, right? The X-ray you cannot see, but you can make an X-ray image by basically converting the frequencies of X-rays to some optical frequencies, optical wavelengths. So it's a sonification. So the frequency of gravitational waves that we are observing now using LIGO is in the audio frequency band, about 10 hertz to a few kilohertz. They have nothing to do with light, with sound. Actually, they are actually disturbances in the space-time, but their frequencies, the changes as well as time, is in the audio frequencies. So we can convert this signal into a sound, and it has this characteristic chirping sound, which is of increasing frequency and increasing.
How precise are they? The sound.
I mean, you have a certain ability to measure these signals, and within that accuracy, it's very precise. It's like it's very characteristic sound called the chips.
Yes. What exciting developments are you anticipating in your field in the next few years?
So there are many things. So in the next, these LIGO and Virgo detectors have not yet achieved their potential sensitivities. We are still improving their sensitivities. And as the sensitivities get better, we are able to see farther and farther in the universe. So the number of signals that we will observe in a year will dramatically increase as we the next 5 years. The next 5 years we will observe thousands of signals. The next 20 years we will be observing millions of signals. So we are observing, getting a totally new way of looking at the universe. So far we have been observing only the coalescence of these compact objects like black holes and neutron stars. But there are other kinds of sources of gravitational waves also. So I mentioned this supernova. That is one possible source that we will observe potentially in the next few years. And there are like rapidly spinning neutron stars producing continuous gravitational waves, like the pulsars that we observe using radios, etc. That's another way. But apart from all these new sources, I am particularly interested in a particular phenomenon now, the last 5 years or so, which is called the gravitational lensing of gravitational waves.
Okay.
So the gravitational lensing is an additional phenomenon that is predicted by Einstein's theory. It's a consequence of Einstein's theory. The theory says, as I said earlier, that gravity basically bends space-time. It curves the space-time. And because the space-time is curved, light that would usually travel through a straight line would also follow the curved path. So basically, gravity would act as a lens to focus light. That's what we call a gravitational lens. And this is in fact, this is the first observational prediction of Einstein's theory that was confirmed with an observation in 1990. It's over 100 years old. A famous observation by Arthur Eddington and colleagues. And we see this gravitational bending of light. Gravity can bend light. And we see now much more dramatic manifestations of this gravitational bending. It's called gravitational lenses. And very massive objects like galaxies basically curve the space-time around it. And if you have a distant galaxy, the light from that distant galaxy will be bent by this foreground galaxy and act as a lens. And because of this focusing, it can produce multiple images of the same galaxy. And this is something that astronomers see every day now. We have several examples of that. This gravitational lensing is a very commonplace phenomenon now in astronomy. So if you imagine it, it's very amazing. Right? This gravity is acting as a light to focus light, but it is regularly now. It turns out that, and also, not only that, this gravitational lensing of light has become a really powerful tool for astronomy and cosmology. People have used this to detect dark matter, to detect planets outside the solar system, to understand the properties of dark matter, all kinds of things. Very, very powerful tool for astronomy. And it turns out that gravitational waves are also bent by gravity exactly the same way. It's like doubly Einstein now. So the situation is the following. Suppose you have a very distant source of gravitational waves, like a merging black hole binary system. And if it happens that there is another galaxy in between us and this distant source, that would curve the space-time around us. These gravitational waves that would have gone somewhere else would also bend and come towards us.
If there is a black hole in between.
If there's any massive object, like a massive galaxy or a cluster of galaxies or a black hole,
because if there's a black hole, it will take the light in it, right?
If it goes too close to the black hole, it would take inside. But if it's outside or even horizon, it won't go inside. It will just bend it. Right. So then there could be multiple paths through which gravitational waves from the same source would appear as. So it's like seeing multiple images of the same source of gravitational waves. But as I said earlier, gravitational waves are more like listening, not like seeing. So they cannot form images of the source. But what we will see is that multiple copies of the same signal arriving to us at different times. Okay. So you would see that, if you have a lens signal, what you would see that you would see one copy of the signal arriving now, and after a few hours or a few days, sometimes even a few weeks, an exact same copy of the same signal will arrive later. So it's like a multiple image same thing. This is something that we have not seen yet, but we very much expect this to happen in the next few years. Because the probability of this happening is something like 0.5%. If you observe about 200 signals, one will be lensed. And we are just about to detect these few hundred events now. And so there's a real chance of observing such gravitationally lensed gravitational waves, and something that I'm very actively working on. Our group is one of the most active groups in the world which is pursuing this one. So we have developed ways of detecting such lensed gravitational waves. We have searched in the LIGO data to look for such lensed gravitational waves. We have not found anything so far, but even the absence of the signals can be used to say something about the universe. So the fact that we have not observed any strongly lensed gravitational waves, or any lensed gravitational waves in the last, about 100 gravitational wave signals, we can say that the universe can have not more than a certain number of black holes, etc. Otherwise, we would have seen it. So we have used this non-observation to put upper limits on the abundance of number of black holes in the universe, etc. So these are very modest upper limit at this point, but this is just providing getting a glimpse of what is the potential of the new field. In the next few years, we are hoping that to observe lensed gravitational waves, and that will just open up another new tool for us to study the universe.
Who's your favorite scientist and why?
Okay, I have many favorite scientists. It's hard to pick one, but there are some people I admire very highly. Think of the living scientists. Krypton is one I would admire very, very highly. Apart from really pioneering scientists who have done pioneering work on different aspects of astrophysics and gravity. He has done everything, right? He has done really pioneering work on different aspects of gravity, black holes, astrophysics.
Even Nobel Prize.
Nobel Prize is something I would say the lowest compared to he has, along with Misner and Wheeler, he has produced one of the most influential textbooks in the study of gravity, book called Gravitation, which is popularly known as MTW, Misner, Thorne, Wheeler. It has helped generations of students and scientists all over the world. And yes, probably he wrote this book while he was maybe in the early 30s. The book has already completed its 50th anniversary. And then he has trained a large number of students and postdocs, so become the most influential people in gravity and astrophysics across the world. He has invested so much in training students, and it's a great mentor. And he is such a popular author. He has written very, very interesting books, Black Holes and Time Warps, very popular, interesting books.
Okay.
And he has worked with filmmakers. He has worked with Interstellar. Basically, he has done anything that one could possibly think of. But even after doing all these things, and in the really the top class way in any of these, he's the top in whatever he does. But he is an amazing human being also. Such a humility, very, very approachable to anyone. It's a real mark of true wisdom, and a very politically correct outlook also. So let me just tell you one anecdote that that really struck to my mind. So someone told me, one of my colleagues told me that this colleague was a TA, teaching assistant in other courses at KIP taught, and this colleague told one day to KIP that there is a student who is struggling in our class, and KIP asked who the student is, and this my colleague told me this black student. He's the only black student in the class, so you know him, and KIP probably said, "No, I don't recognize my students by color." So it just reminds us when we occupy privileged positions, positions of power, etc., how important it is to be a very, very responsible person. I think it's a great example.
If you could solve one scientific mystery right now, what would it be?
There are lots of scientific mysteries. I have no idea of what. But certain things are even beyond my comprehension. But if I was thinking of in this sort of something in the domain of tractability, I would say I'm very curious to know what dark matter is. So we are, because unlike what is called the dark energy, which is driving the accelerated expansion of the universe, we had pretty reasonable ideas of what dark matter could be. It's very popular even 10 years ago. This dark matter is this unseen matter that exists in galaxies and so on, and we see its effect on other luminous objects by its gravitational interaction, by the gravitational force that it applies on other objects. So we see extremely strong evidence from a variety of systems. The dark matter exists in the universe. It forms a significant part of the total matter in the universe. And there are multiple candidates of what dark matter could be. There could be one idea that there could be some fundamental particles that are beyond the standard model of particle physics. And another very complementary approach is that there could be some large number of very small black holes or primordial black holes, different sizes. And in the last 20-30 years, people have, experimentalists, observers, astronomers have been trying to find evidence of dark matter in any of these forms, but none of them seem to have worked. So, until 10 years ago, 15 years ago, we were all hoping that we are on the verge of detecting dark matter. But it seems that all these things are really kind of stopping somewhere. Yeah. So it really has become a major puzzle, and it is a puzzle because it seems to be a tractable puzzle. So I would really like to know what dark matter is.
What improvements or changes would you like to see in science education in the country?
It's a very difficult question. I don't think I have the right expertise to comment because I don't think I have a grasp of the full picture. But I could see some aspects. For example, our system is very much based on sort of rote learning. We like to mug up things. We are expected to mug up things and reproduce in exams. And that basically kills the curiosity of people. And it probably make them distance them from sciences also. While eventually this is not the way science is done, right? It is a curiosity-driven inquiry with a very simple systematic approach. You basically rely on logic and evidence. And the scientific method is just that. It is just like something, ask a question and try to answer it based on logic and evidence. It's a systematic way of doing it. And it's something that we all try to do in life in any applications. And it is not taught in that way. It is taught as a body of facts that we all have to mug up and reproduce. And it would be, it is harming a lot of people in the whole system. So I would like that to change. But, it is easier to be said than done. So we have a number of challenges to address. And I'm not saying that there is an easy solution.
What advice would you give to youngsters who are starting out in science?
Again, I am not qualified to give advice, but I can just look back and what was it like when I was at that stage. So when I was in college and so on, it was in that time of IT boom. You're probably too young to remember this Y2K, all these things. So they were engineering and in computer science, etc. were the things that everyone was asked to do. So all my teachers and most of my neighbors and etc. all said that were just advising, pushing people to do engineering and so on. But I had no knack of cracking competitive exams, and also I did not do very well at university. But I had no interest in doing those. But I was sure that this is not what I want to do. I'm not saying that I knew what I wanted to do, but I was pretty sure that this is not what I want to do. I had a firm belief that even if you have a strong interest in something, if you pursue it, there is a possibility of living in the world and contributing to it without worrying about this competition. So one thing I did right was, in that sense, follow my conviction that I don't have to be part of this rat race. So I think I would advise that if you have a strong interest in whatever you do, it's okay to pursue that. Of course, everything requires hard work and dedication. And with that strong motivation and hard work, with a little bit of luck, people should be able to succeed in what they do.
What do you find most fulfilling in being a scientist?
It's a hard one to answer. Fulfilling is a hard thing to say. I can say what is the privilege. The privilege is that you have the privilege to make an earning pursuing something that you are interested in and curious about. It is a privilege that you are paid to pursue your own curiosity. Of course, there are limitations to what we can do, and we have to do all responsibilities of teaching and testing. But one thing I really enjoy these days is to working with young people and our students and postdocs, my young colleagues, discussing ideas and seeing that creativity emerging. We will criticize and kill these ideas, but eventually someone will survive and pursue them and lead services. So I really enjoy this process of these intellectual churning that is happening in our group and elsewhere. That is something I really look forward to and enjoy. So that's, I would say, something I really enjoy. And fulfilling is, I think, it's a loaded word, because to feel fulfilled, you have to make a contribution that you think is a better contribution. I think I'm not yet there. So I'm
Maybe after
enjoying what I'm doing. I think
after figuring out dark matter.
I think it takes a lot more effort than mine.
Lastly, we ask all our guests for their favorite popular science book recommendation. If you could recommend one.
I would very strongly recommend Cosmos by Carl Sagan. And Carl Sagan is another one I have a great admiration. And it's also one very rare example of how a television series is actually better than a book even. It never happens that if you can make a movie or a television out of a book, you always have an inferior result. But this is both the book as well as the television series Cosmos are really absolute masterpieces. And I think everyone should watch them and read them. And it covers a whole spectrum of human endeavor. It is not only about science; it includes philosophy, history, literature, art. And Carl Sagan is such a remarkably deep as well as broad person who seemingly go from one topic to another, making this very, very beautiful and profound connection. And I can't have enough of that.
Thank you. Thanks so much for your time.